Okay. All right. Before we write down these rules here, let me run through these first, and then you guys can have a chance of attempting to write these down from memory, at least your first try at it. Okay, but if you can turn to page 8 here. Sorry, page 7. Let me go through these important rules here. Some of these are review. We should know power rule. We've been using that a lot for derivatives. Our six original trig derivative rules. We should have these memorized. This is from last semester, and also these are so important because if we're working backwards from these, we are essentially looking at integral rules as well. So these are actually 12 rules, right? These are the same as these below, right? We're just going from right to left instead of from left to right for our integrals. Okay, e to the u du, we definitely need to know this. This one we've been working with here. Natural log of u is u prime over u. Okay. I know we've seen this before, but I won't have this show up on the quiz. So, and these we can kind of just not have to worry about for the quiz. All right, integral rules. We should know power rule. We've been using that a lot. Trig integrals, we should know that as well. These, again, we're not memorizing these, right? We're just working with these original 6, right? 1 over u du, we should know this as well for natural log. E to the u, we should know this as well. And then what we just learned yesterday was this one, right? This one looks a lot like e to the u, because e to the u and a to the u, they both have the original original equation show up, but there's a conversion, right? And the conversion is going to be 1 over natural log of a in front of a to the u. Okay. Yeah, we do. Yeah, these are ones that we went over from 5.2, and these are trig integral rules that do not show up on the original 6, right? We don't have tangent, cotangent, secant, and cosecant. Those involve natural log. Okay. So let me let me see if we can talk about how to memorize these. So you know that first off, these 4, since if trig integral rules don't show up in the original 6, you know it has to be natural log. Okay, so tangent, cotangent, secant, and cosecant. Let me start off with this one here. Secant and cosecant, they both involve natural log. The way I remember it is, I know that secant's derivative has secant tangent in it. And then that helps me remember, okay, I know secant tangent is going to show up, but it's going to feel a little bit different because it has natural log. So I just know I'm going to put a plus between it and separate it that way. Okay. So that helps me remember. I know there's natural log involved. I know it's going to look a little bit different. It's not going to be secant tangent, so it's going to be secant plus tangent. Okay. Now, cosecant's derivative has this look to it. Cosecant is negative cosecant cotangent. We should know this as well. And but we know that integral of cosecant has natural log in it. The negative is going to stay there as well. Instead of cosecant cotangent, it's cosecant plus cotangent. Okay. So that's the way I remember it. I know what the derivative looks like, and I know that I just have to adjust those components to fit into my new rules. All right. Next up is tangent and cotangent. Now, tangent is negative natural log of cosine of u plus c, and cotangent is natural log of sine of u plus c. The way I remember tangent and cotangent is I know that tangent can be rewritten as what? Sine over cosine. And if I were to do this problem from a u substitution perspective, I would choose the denominator as the u value. And then if the denominator is the u value, the numerator cancels out. I end up with 1 over u du, and then ends up being natural log of cosine of u plus c. Now, there's a negative that shows up. The reason the negative shows up is because the derivative of cosine is negative sine. So there's a negative that shows up from cosine. So that's why there's a negative here. Now, cotangent. Cotangent, if we rewrite cotangent, cotangent is what? Yeah, cosine over sine. And if I let the u value be sine, sine's derivative is a positive cosine, so that cancels out. I'm left with 1 over u du, and because sine is a positive cosine, I don't have any negatives here left over. It's just going to be natural log of sine. Now, keep in mind though that our tendency is we're going to mix these up because we're just used to seeing cotangent producing something negative, and we're used to tangent producing something positive. So this is going to feel a little backwards here. Right. So this is a trouble spot that students can experience. Okay.
You're like not the antiderivative.
I'm sorry?
You're not the antiderivative though, right? That's like not the regular derivative.
So these are right. I'm connecting this with the derivative rules, right? Because derivative, we associate derivative with tangent with positive secant, with a positive derivative, and we associate cotangent with a negative derivative. And so I'm saying that's the reason why students tend to mix these signs up, because right, because it's opposite from what we would expect. Right. Okay, so why don't we take a first stab at these rules here? Page 9 here.
Would there be a section like this on the quiz tomorrow?
No, there won't be.
Kind of like no, you know.
Right. Yeah. Okay, so integral of u to the n, this is just what? Power rule, right? So power rule is just u to the n plus 1 over n plus 1 plus c. Right, maybe we don't have to write this out or memorize it in this form. You guys already know what to do, but this is what the official rule says. Okay. All right, what about 1 over u? What's the integral there?
Ln.
Yeah, natural log, right? Natural log, absolute value of u plus c. E to the u. That's the derivative. So it's just e to the u plus c, yeah. The u prime is self-contained within that du, so we do it for the derivative side, but not for the antiderivative side. All right, tangent. The tangent, whenever I see that, I'm just thinking, okay, that's really sine over cosine, right? And what's going to show up? I know it's natural log. Is natural log of what? Of cosine, right? But this one's a little backwards, so there's something what in front? Negative, I know, yeah. All right, cotangent. Cotangent, we can think of cotangent as what? Cosine over sine. So that helps me remind myself that it's the sine that's going to show up in my natural log antiderivative. And this one is positive. Okay, secant. The way I remember it, I know secant's derivative is secant tangent, so I know that secant and tangent are both going to show up in my antiderivative rule. So I know it's also involving natural log because it's not one of the original 6. So natural log absolute value of secant of u plus tangent of u plus c. Now secant we associate with positive, so this one doesn't feel backwards. This is what we would expect. Okay, cosecant. When I think of cosecant, I think of cosecant and cotangent as part of the derivative. So I know this is one of the new ones, so natural log is involved. But this one has a what in front? Negative.
Why did that have a negative in front? It's like, usually it's like the opposite.
Well, I would say that tangent and cotangent is going to feel opposite, but secant and cosecant is going to kind of follow along with what you would expect from a derivative. Yeah, I'm not, we're not going into the proof of it, so we should kind of take it from a memorization standpoint. Okay, a to the u du. This is an exponential function, right? Exponential function is related to e to the u, so these are similar in the sense that they're both going to produce the function itself. But this is not base e, so what's going to be in front of it? Yeah, 1 over ln of a. And then the original function shows up plus c. So I do want to see, I do want to make you feel like as if, you know, you're working with something that is familiar, right? Because e to the u is itself, a to the u is also itself, just with a little bit of something extra in front. All right, let's work through some of these problems here. The key is attached, so if you're working ahead, feel free to check your answers and move at your own pace. All right, so number 1, 1 over 2x plus 3. I always want to go down my list of options here, and I realize my first option should be power rule expansion, but too many terms in the denominator. I'm stuck in this form here, so I got to look at u substitution. Right? What could be our u value? Okay, make our substitution. Push out what in front? Out the 1/2, and then we're left with a rule that we recognize, right? All right, number 2, I would like to expand, but I can't. My denominator kind of forces me into something that I can't, right? I can't separate. So I'm stuck in that form. U substitution is my next option. What's our u value here?
The denominator.
Yeah, the denominator, right? And do we expect the x to cancel out down the road? Yeah, that 4x squared is a good degree for that to happen, right? Okay, number 3, can I expand this one? Yes, because denominator only has what? Only has one term, right? So let's just go ahead and split up into 2 problems and then see where that takes us. Okay, we couldn't do that with previous ones because it had multiple terms in the denominator. Okay, so we can just clean up as best as we can. So this becomes 2 minus 5 over x dx. Okay. What can we use with the first one here? What rule do we use for 2? Or what does 2 become? That's derivative, right? What's antiderivative? 2 what? 2x. 2x over 1, right? Yeah. And then what can we use for 5 over x? Well, if we bring the denominator to the top, we get 5x to the negative 1. If we do 5x to the negative 1, if we do power rule, we get 5x to the 0 over 0, right?
Just 5x over x squared.
No, what is it?
Just 5.
How about this way? What if I wrote it a different way here? What if I did this? That make it feel more recognizable? Right, if I push the 5 out, what's the rule for 1 over x? Natural log. Yeah, that's it. Right, there's no need for u substitution. This is just x, right? So this matches perfectly with this rule here. Right? So, yeah. Now we do need to feel comfortable with rearranging it. If we can't recognize this, you can always rearrange it into something that feels more familiar. Right? Okay, so power rule here, natural log here. 2 becomes 2x. The 5 stays, natural log absolute value of x plus c. Okay, we'll skip number 4, come back to number 4. Yeah, we'll come back to it. All right, number 5. There's only one term in the denominator, but I mean, there's only also one term in the numerator here. So it's not like splitting up is going to help us any further. It's not like we have multiple terms up top we can separate. So it looks like this is going to be a u substitution problem because it's too complicated for any one rule to handle. What could be our u value? Yeah, natural log of x. The derivative of natural log of x is 1 over x, and that should handle that x in the denominator here. So okay, so those are the pieces that I'm finding substitutions for, and then hoping that this x will pair itself up down the road. So u equals natural log of x. Du dx. Natural log of u is u prime over u, which is 1 over x. Solve for dx. Make our substitutions here.
How come you're not using the squared?
Oh, as part of the u value.
Yeah.
It's going to be a little bit too much, and also typically, whenever we're searching for a u value, we should consider what's inside the parentheses as our first option. And then if that doesn't work out, then we can maybe consider what's outside the parentheses, but usually, again, I'm speaking all these in general terms because everything I say, there's always an exception, but we always want to look at what's inside the parentheses. Okay, and another reason is we don't want to include that 2 there, because if we include that 2 there, then the derivative would be a whole chain rule, and the chain rule is going to be too much for that x to manage. Right? So it is also a little bit of kind of looking at to see, do we have something for the derivative to pair up with? But this one works, right? The x's cancel out, and what rule can we use to handle this one? What rule can we do for u squared?
Power.
Oh, yeah. Or you can leave the 3 below under the parentheses, under the natural log if you want. It's up to you. All right, number 6. I can't expand, right? Too many terms in the denominator. So we got to look at u substitution. What could be our u value here? The denominator is going to be too much because the denominator will produce derivative that has no pairing for the rest of the problem. Yeah, in the parentheses, right? So we know that, we have to save something for the derivative, right? So the root x is what we're going to save, and the 1 plus root x is what we're going to have as our u value. Okay. What can I do to get this ready for my derivative step?
The root to 1.
Yeah, to the 1/2. Okay. All right, 1 goes to a 0. X to the 1/2 is power rule, so 1/2 x to the negative 1/2. All right, I do want to cross multiply and solve for dx, but let's clean that up first. I want to make that look as close as possible to what I want to cancel out, just makes it visually easier. So I'm going to rewrite this. Du over dx is equal to 1 over 2 x to the 1/2. Right, I'm resolving that negative exponent, and I can make this x to the 1/2 turn back into what? Square root of x, right? And the reason that I want to do that is because I'm looking to see, right? I keep looking back at my problem to see what will make it easier for me to match up. Okay, cross multiply. Oops, 2x. I'm sorry. I completely wrote this whole thing wrong here. My bad. It's d over dx, not dx over du. Okay, du over dx, sorry. Cross multiply. Make my substitution. The dx gets replaced with this. The 1 plus root x gets replaced with u. And then we're hoping that this root x will pair up nicely once we make those substitutions. All right, do the x's go away? Yes. Right. Okay, what can we push out in front? 2. So we're left with du over u, or you can write it as 1 over u du. Okay, what rule do we use for this? Not power rule. Yeah, natural log, right? 1 over u. Power rule will be any other power. If it's used to the 1/2 or used to the square, but if it's used to the first power in the denominator, if we try power rule, it's gonna mess up because we'll get u to the 0 over 0, and hopefully that will help remind us, oh, there's something else that's going on here. Okay, page 10. Yeah, we'll come back to 4. I want to do, yeah.
Do you have the trig ones?
Yeah, we will. It's coming up. Let's see. 7 and 8. Can you tell what 7 and 8 are? You're both synthetic division, right? Power rule doesn't work. Use substitution doesn't work. Synthetic division has a certain look to it, right? And hopefully, if we see enough of it, we can kind of just recognize, okay, this is the synthetic division. Let's just do number 8 then. No, they're both the same process. All right. So what would your first step be?
Yeah, the x plus 1.
Yeah. Set that equal to 0. Find that factor. All right. First row of numbers. Yeah. So we have 1. 1 is for x cubed. Next is -5 is for x squared. Next is 1 is for the x. -2. Do we have any degrees that's been skipped over? No. So this one's okay, right? If there were skipped over degrees, you will have a 0 for that variable that's been skipped over, or that degree that's been skipped over. Okay, let's remember the process here. First thing, we drag the number down below the line. Then we do what? Multiply.
Yeah.
And then add. So -1 times 1 is -1. -5 plus -1 is -6. Multiply again. -6 times -1 is 6. 1 plus 6 is 7. -1 times 7 is -7. -2 minus 7 is -5. Okay. Remember that we start off with x cubed. So what are we going to start off here then? Remember, we're dividing by x, right? So we're fall by 1. So x squared. Okay, now we can fall by 1. X squared, then it's x, then it's the constant, and then it's the remainder. So this is our new problem that we're going to do. The integral of this dx. So this is our new problem that's easier to work with than this. So this is the exact same thing as this, just written out in a form that's easier for us calculus-wise. The first 3 terms, we can simply use what? Power rule. And the last term is just use substitution, but it ends up being natural log, right? You can reduce to 6 over 2 if you like. On the key, I worked out the full U substitution step if you want to see that, but if I see a U value that is this simple, I see it's in the denominator raised to the first power, I can jump from here to here. Okay, number 9. Too many terms in the denominator to expand. What could we do here? U substitution. Okay, what could be our U value? Yeah, 2x plus 3. Okay. I can think of this as 1 over 2x plus 3 squared times dx. If I make my substitution, the dx becomes du over 2. What can we push out? Mhm. All right, what rule do we use for this?
Well, it's not log, natural log. Right?
Good. It's not natural log because why? It's squared.
Power.
It's power rule, right? But what do we need to do before you go through power rule? It needs to be u to the what? Numerator. So u to the -2, right? So I do want to. The reason why I had this problem here is because I think we see 1 over u so much that we're going to think that it's natural log every time, but just be careful, right? That if it's raised to any other power, we got to force it up and go through power rule. We can't just leave that and do natural log, okay? Even though it feels like, we're kind of accustomed to that because we've done it so much, but watch out for that power, right? That power is going to determine what rule you're going to use. Okay, so you're right, power rule. Okay, add 1 to the exponent, divided by the new exponent. Okay, so -1/2, bring the u back down to the denominator, replace the u back with x. Okay, number 5. So number 10, integral of 5 to the secant of x, secant tangent x dx. You see an exponential function here. Yes. Yeah, 5 to the secant x, right? So what could be our u value here? Secant x, right? We're kind of seeing the a to the u rule kind of form here for us. Dx as well, right? And will that secant tangent go away, you think? Yes, the derivative secant will take care of that, right? Sorry, u equals secant x. So 5 to the u, that's a to the u. So the rule for a to the u is just a to the u with a little bit extra in front, right? So we have 1 over natural log of a times a to the u plus c. And then replace the u back in terms of x. Okay, number 11. Do we look at the bounds initially? No, ignore the bounds, right? The bounds is not part of the process. We got to take care of the in-depth integral before we do anything with the bounds. I'm going to rewrite it without the bounds so we're not distracted by them. So if this is your problem here, too messy for one rule to handle, we got to look at u substitution. What could be our u value? Yeah, so if we do that, then we kind of see the connection with e to the u, right? We kind of work towards that e to the u rule. And that exponent should handle that x pretty well. the 2 comes down, which cancels out with the negative, with the 1/2. X squared becomes X. The X's do cancel out, but there's a leftover what? -1. All right, so do we have a rule for e to the u? Yeah, e to the u. Well, we would do plus c, but then now we have our bounds, right? So negative e to the u, this is our antiderivative. But what should we do before we bring back the bounds? Yeah, let's bring the x variable back, right? If we start inserting the bounds now, then you're putting x's in for u's, and that's a little bit of a mismatch, right? So bring back your original x variable. Now I can do a half bracket. Now I can start looking at the bounds, right? Upper bound first, followed by lower bound. Okay, √2 squared is just 2. 2 divided by 2 is 1. I'm just left with this -1 here. Now, what's e to the 0? 1. Yeah. Just be careful. I think sometimes when we see 0, I think our natural tendency is, oh, that's going to wipe everything out. It wipes some things out, but it may not wipe everything out, especially if that 0 is being inserted into the exponent. Right? If the 0 is inserted into a coefficient variable, then yeah, it will wipe things out. But just be careful that you're convincing yourself things are getting wiped out before you commit to that. Number 12 is the same thing. U substitution. What's the u value? Yeah. And you go through the same process. It's a little bit easier of a problem. Let's skip that one. We'll come back to it if we have time. Let's look at number 13. 13, tangent x plus secant x plus cotangent x plus cosecant x. Are these all separated? Yes. So they're not connected in terms of, we don't have to go through U substitution for these, right? These are 4 separate problems. So we just have to identify the integral rule for each of these, and it's just attached to that.
You don't have to identify.
Say it again?
You don't have to identify.
Yeah, that's right. Yeah, so that's it, right? So this is just a practice of the new rules that we learned, right? So let's see if we can recall. Tangent is sine over cosine. These are all the new log rules. So tangent is what? Yeah, natural log, absolute value of cosine of x. But there's something that's a little bit strange here. There's what in front? There's a negative, right? Secant also involves natural log plus, yeah, tangent x. Cotangent is similar to tangent. We can rewrite it in terms of sine and cosine. Positive. So positive what? Natural log, absolute value of what? Sine. And then cosecant is minus natural log. Yep, good. Plus c. Okay, 14 looks messy. It's obviously U substitution. No rule can handle with that much complexity in it. What's going to be our U value? Or, yeah, the exponent, right? So we can see that exponential function show up, right? If we're able to kind of zero in on that, we kind of helps us identify. Okay, is that going to take care of this pretty well? Yeah, that exponent 3 should handle that exponent 2. But to find this derivative, we have to go through a little bit of what? This chain rule, right? So outside derivative. So parentheses cubed becomes parentheses squared, or 3 parentheses squared. Keep the parentheses intact, times, what's the inside derivative? -2, right? Yeah. I'm going to multiply the 2 and -3 and -2 together. But the 5 minus 2x squared, that's a good sign, right? We see that that's waiting for us to pair up. All right, do the x's go away? Yes, there's a leftover what? Negative 1/6, yeah. Okay, so now we just follow the rule for a to the u, right? So negative 1/6 is gonna stay. There's a coefficient of 1 over natural log of 7, and then 7 to the u plus c, and then replace the u back in terms of x. Because anytime you're picking an exponent, make sure you keep the entire exponent. Otherwise, then you're left with 7 to the u cubed, and we don't have a rule for 7 to the u cubed. We have a rule for 7 to the u, so that forces us to take the entire exponent as our u value.
Could we keep it unsimplified?
Yes, you can. Yep, this is fine. That's fine. Just make sure you bring the u back in terms of x. Yeah, you can leave all this unseparated if you want.
We don't have the exponent of the x.
Yes, yeah, you can do that. I know it's a little bit strange here, but yeah, this is an exponent on top of an exponent. Yeah, that's right. So this afternoon, I'm going to go over worksheet 2. Tomorrow morning, I'll do morning review. And then tomorrow, beginning of class for 10 minutes, we'll run through the rules, and then we'll do 1 or 2 problems, and then you'll take the quiz. Okay, 6 problems. All right, come get your phones.
Like we're learning about like aggregate supply, aggregate demand, like demands of everything. I think it is like. Yeah, I think you're both saying the same, but it's harder, like, that's the hard skill, like, it's actually just a lot more greater than that stuff. So it's like, it's even stricter on labels for us.
I was fine.
We thought he was already 6 and 2 and he was part of the labels, but he's like, no, these graphs are more complicated, like, so like, he's still learning this for later. Okay.
So I'm just really trying to.
Okay, yeah, just keep me updated. All right, thanks. Appreciate it. Thank you.
Maybe something you can. Hey, you guys today? Good. And good. I mean, I want to let you know, I'm gonna be outdoor St. Friday because I'm gonna be out of town for an audition.
This week?
Yeah, this week. I'll be here for quiz Wednesday.
Right. We are going to, let's see. Oops.
I assume we're learning stuff. So, yeah.
Yeah, different equations. So basically, we're just take the integral on both sides of the problem. So you'll do problem like.
So it's like implicit.
Yeah. It's basically like. having to do power rule on both sides.
Okay.
So this one would just be x cubed over 3 plus x. And this one would just be y squared over 2. And then we'll just put a plus c.
Yeah.
And just algebraically just try to solve the one.
I assume you get more like complicated too, like there's like log, natural log involved.
Yeah. So the reason why this gets more complicated is now you have to worry about both sides and trying to do power, trying to do integral from both sides. It feels like two problems in one.
Also, you're trying to just like solve for y.
You should solve for y.
Okay.
So you got to here. So once you're here, you would multiply by 2, take the square root.
So it won't be an exact number, right? You'll still have the x and c.
Yeah. But then you have to solve for c in the given order pair.
Okay.
So that's what we're doing on those.
Is there any graphing involved?
Mhm.
Is there any graphing? No graphing. Okay. Austin, did you place any bets on Super Bowl?
No.
My parents said you just